Today we're going to be continuing on our topic of air pollution, but we're going to extend this topic to how it is that air pollution relates to what goes on in water. And so to start that topic off, we're going to continue where we left off last time, which is the topic of acid precipitation. We're looking here at a lake in the Adirondack Mountains of northern New York State. This, like many of the lakes in the Adirondacks, although they look perfectly beautiful, are largely devoid of fish life. The water in them is so acidic as a consequence of many years of acid deposition that the water has become too acidic to support many different kinds of fish species that can't tolerate high acidity. If we travel up these Adirondack Mountains to their higher elevations, we encounter spruce fir forests like you see here. But if you notice, a lot of these trees are not looking very healthy, and some of them are just completely dead. That is also a consequence of long-term acid precipitation, which has a number of effects on these spruce fir ecosystems. The acidity can damage the leaves directly, for example, but it also has a more insidious effect on the soil that these trees grow in. By acidifying the soil, certain of the nutrients in the soil, notably calcium, are leached out, making this a system which is too nutrient poor to support healthy spruce trees. Now let's turn our attention to a different kind of environment, the urban environment. Notice in this case, in this photograph here, this heavy pall that's hanging over the city. This is a phenomenon which occurs fairly commonly in the west coast of the United States, although you can also find it in other parts of the country where cities are built in basins or have some kind of obstruction like a mountain range next to them. In these kind of situations, temperature inversions can become established. Now, under typical kinds of circumstances, as ground heats up during the course of the day as sun shines on the ground, it makes the air above that ground less dense as it heats. Consequently, that warmer, less dense air rises and cooler air comes in to replace it underneath. So a convection cell builds up. In certain kinds of situations, however, this normal tendency of air above the ground to heat up and move away is interfered with. So in situations where a high pressure system locks over an area, similar kind of thing can happen when a body of warm air settles over an area, particularly when that area is in some kind of a basin or valley or near the coast, where a mountain range to the east of this city might interfere with movement of air. And this is exactly what we see on the west coast. Many of those west coast cities are bounded on their eastern border by mountains. And in these kinds of situations, normal convection is interfered with. And so the surface air under this cap of high pressure or warm air is trapped, and all the pollutants that are generated by a city are trapped there and build up over time. And so the air becomes progressively less healthy to breathe. And sometimes these inversions can go on for days. Particularly in the summertime, we see these phenomena occurring. Now, even on a more intimate scale, one can find pollution building up within particular buildings. and not necessarily just in a city, but even in the country. Situations can develop where households, especially new houses which are very tightly sealed, can have pollutants build up in them. So various kinds of household chemicals that we use to clean and things like that, bleach from our washing machines, all these various sorts of chemicals can build up in a tightly sealed up house. Another phenomenon is a consequence of what kind of substrate the house is built on. So houses that are built on rock ledges, particularly when those rocks are granites and things like that, these rocks have a certain amount of radioactive material in them. So when houses are built on bedrock outcrops like this one here, then we can find that in the basements of these houses, the radioactive decay of some of these minerals will release the element radon, which exists as a gas. And this will build up in the basement and then make its way through the rest of the house. And again, this occurs specifically in new houses, places that are very tightly sealed in order to conserve heat energy in the wintertime and to keep the house cool in the summertime. Although that's very good for those sorts of things, it's very negative for buildup of radon in the house. Now notice also on this image here, these striations you see moving across the surface of the rock. This is a consequence of a different issue altogether, but it's worth mentioning now. Those are grooves left in the rock from glacial times, as glaciers scoured the landscape of the northern parts of the United States and pretty much all of Canada. Any bedrock outcrops that were ground over by an ice sheet was left with these kind of grooves in it. On the other hand, old construction, like this 19th century barn, tend not to have a problem with buildup of radon. They're often built on stone foundations like you can see here in this photo also. And these stones have little gaps between them that allow the radon to escape from the basement in the case of a house, or anywhere in the building in the case of a little barn like this. So although old construction is much less energy efficient in terms of holding in heat in the wintertime and things like that, they are safer from the perspective of buildup of radioactive materials like radon. To combat these sorts of air pollution issues that we've been talking about, by 1970 the federal government had passed legislation that established air quality standards for the U.S. It focused primarily on emissions of lead and particulates, as well as sulfur dioxide, carbon monoxide, nitrogen oxides, and ozone, all of which we've talked about. One big thing that happened was that by the 1970s, leaded gasoline was being phased out, and now it's completely gone. And that has resulted in the vast majority of atmospheric lead disappearing. Also, roadsides where lead would tend to build up, those levels of lead are also declining now. It's been quite a few decades since we've had this elimination of most lead emission into the atmosphere. Now, the Clean Air Act did not just affect lead dramatically, however. The Clean Air Act has also had a dramatic effect on sulfur dioxide emissions into the atmosphere. And that has resulted in a reduction in acid rain in portions of the country. Now let's turn our attention to an atmospheric phenomenon of a different sort, the one that has given rise to global warming. What you're looking at here is a photograph of a glacier in the Rocky Mountains of the western U.S. And what we are seeing in glacier systems like this one is that every year they get smaller. Now, of course, they're much smaller than they were during Ice Age times, but the rate at which they are shrinking has rapidly speeded up in recent decades as a consequence of this phenomenon that falls under this broad umbrella heading of global warming. Let's see what we mean by that. Global warming is the consequence of the buildup of greenhouse gases in the atmosphere. And these are all gases that we've talked about before. Things like especially carbon dioxide, but also methane and nitrogen oxides, as well as tropospheric ozone. These are the ones that are best at reflecting infrared light coming from the sun back towards the Earth's surface. So it works a bit like panes of glass on a greenhouse, where solar energy is permitted to enter the greenhouse, but then it is reflected back by the glass into the greenhouse, which keeps the inside of the greenhouse warmer than it otherwise would be. So the Earth's atmosphere, when charged with these gases, does a very similar kind of a thing. Now, much of the energy that is trapped gets transferred to the ocean because water, with its high specific heat, has a great capacity for absorbing thermal energy. The downside of that, even though it does help to keep our climate cooler than it otherwise would be in the presence of this greenhouse effect, it does make the oceans themselves get warmer. And as the oceans get warmer, then we see things happening like pack ice in the Arctic start to melt. Here's a graphic produced by one of our federal agencies charged with looking at the greenhouse effect that illustrates how this occurs. You can see here solar energy coming into the Earth and then being reflected by the Earth's surface. In the absence of large concentrations of greenhouse gases, much of this solar energy reflects back out into space. But with an increasing concentration of greenhouse gases in the atmosphere, more and more of it gets reflected back towards the Earth's surface. Now the question becomes, how do these greenhouse gases accumulate in the atmosphere? And the answer appears to be that much of the reason for the accumulation of these gases has to do with human activities. In particular, use of fossil fuels, which when burned release carbon dioxide into the atmosphere. Other kinds of processes, however, like forest fires or other kinds of human-set fires, and even things like cutting down forests, where all that carbon that's stored in the trunks of trees, as this material gets used, either by burning it or by simply stopping the living trees from removing carbon dioxide from the atmosphere, these sorts of things make atmospheric carbon dioxide levels go up. Now, if we look at the historical record, before the Industrial Revolution of the late 1700s, early 1800s, we can, by looking at various lines of evidence, conclude that atmospheric CO2 concentrations were about 200 parts per million. But since the Industrial Revolution, when fossil fuel use greatly accelerated, atmospheric carbon dioxide has done nothing but go up, so that by 2007, CO2 levels were almost double what they were before the Industrial Revolution. And in the years since then, the CO2 levels have increased still further. Here's a graph produced by NOAA that illustrates the rise in greenhouse gas concentrations in the atmosphere from the 1970s to about the year 2010. Notice that the relationship is almost linear, and that over these years, just in a few decades, we've seen almost a doubling of greenhouse gas concentrations in the atmosphere. Here's some additional NOAA graphs that illustrate the relationship between carbon dioxide concentrations in the atmosphere and temperature of the Earth. So, as we've discussed previously, the concentration of carbon dioxide does go up and down during the course of the year as a consequence of the Northern Hemisphere photosynthetic season, the summertime, when CO2 gets removed from the atmosphere by photosynthetic organisms. But then in the Northern Hemisphere winter, the concentrations of CO2 go up when photosynthetic organisms are no longer taking it out at the same kind of rate. And keep in mind that much of the Earth's land surface is located in the Northern Hemisphere, so that's why it's most related to the Northern Hemisphere photosynthetic season. So the relationship we see here is a direct one. As CO2 levels have gone up, temperature has gone up. So now we can ask the question, what are the consequences of this global warming phenomenon? And we could cite the following sorts of things. When you add energy to the atmosphere and to the oceans, this increases the amount of kinetic energy of molecules. Remember that temperature is a measure of the average kinetic energy of molecules. So as we have greater kinetic energy, that leads to greater unpredictability in the Earth's weather. You can expect by adding additional energy to the atmosphere that you will also generate more frequent and more catastrophic sorts of storms. And already we've seen evidence that that is indeed occurring. Famously, the mayor of New York City a few years ago said that we now have the 100-year storm every few years. The 100-year storm being that storm which is the worst storm that we might expect in a 100-year period. Global warming also leads to polar ice cap melting and glacier melting. And this contributes to sea level rise as you take more and more water that's been locked up in ice for thousands of years and release it into the ocean. Not surprisingly, more water means higher sea levels. As you warm the ocean waters, you also have the phenomenon of thermal expansion taking place. As water increases in temperature, its density actually goes down. The greatest density of seawater is actually reached at several degrees Celsius above the freezing point, 0 Celsius. And as water warms further, it expands further. And this phenomenon alone accounts for much of the rise in sea level, even beyond the effects of melting ice and putting that into the ocean. As we thermally expand water, it makes sea level rise as well. And current predictions are that over the next century, we could see as much as 59 centimeter increase in ocean levels, and that would lead to the inundation of many low-lying coastal areas and coastal cities. Here's a map of the Earth's surface that is generated by NOAA from one of their climate models that illustrates the change in temperature that's expected across the planet over the next 50 years. Notice that the greatest changes in temperature occur in the Arctic, the northern hemisphere Arctic, but also we see increases in temperature over much of the Earth's land masses, less so over the oceans. However, notice that there are a couple spots that actually will be cooling over this same period. Look at that little area just to the south of Greenland. As you melt polar ice and put it into the ocean, that portion of the North Atlantic can actually see a decline in temperature, and that is a cause of some significant concern all by itself. By chilling the North Atlantic, you could conceivably shut down the ocean conveyor belt that brings all this warm tropical water to Western Europe. It is thought that that's what happened at the end of the last ice age. All of the glacial meltwater that was collecting in this gigantic lake in northern North America burst through its dam and entered the North Atlantic in a very short period of time, and that set off a little ice age again in Western Europe, which lasted for some time after most of the world's ice age was over. Here is a map of the plant hardiness zones of the United States as prepared by the U.S. Department of Agriculture. This particular map is from 1990, and it provides planting guidelines for farmers and homeowners as to what kinds of plants will be hardy in a particular region of the continent, and also what times of year might be the best times to plant things. Now, notice especially across the northern part of the country, you see these white areas in northern Maine and across the northern plains. These are what would be zone 3, the coldest of our hardiness zones across the country. Let's compare that with the most recent plant hardiness zone map. Notice in this map that zone 3 has shrunk in its distribution. In this map, zone 3 is represented by the pale lavender at the top of the map. And notice that in northern Maine it's now only spotty in occurrence, and across the northern plains it's also reduced its extent quite a bit. In addition to that, if you look at the other hardiness zones represented by the other colors, especially in northern parts of the country, these zones have expanded northward. Here is a color key that goes along with that map. Notice especially zone 5. In zone 5 you can expect minimum winter temperatures down to about minus 20 Fahrenheit. Now this is a notable temperature because there are a number of kinds of plants that will not survive that kind of cold, and so they cannot expand their ranges into zone 5. And this includes not only wild plants but also cultivated plants, ornamental kinds of plants that people might want to have around their houses. So here across the northern portion of the country, plants like the redbud tree, which is a popular ornamental, and hollies and things like that, places where we didn't used to be able to plant them, they now survive the winter. So there are several observations that one can come away from this map with. One is that if we were to melt the ice sheet over Greenland, it would be an event comparable to what happened toward the end of the last ice age, when all that glacial meltwater hit the North Atlantic. If all that fresh water locked in Greenland hits the North Atlantic, it will reduce the salinity of the ocean and thereby shut off the ocean conveyor belt that brings warm water from the Caribbean to Western Europe. Now, if we look at a map of Western Europe, much of it is actually to the north of the United States, and yet the climates that they experience are fairly mild. If that flow of warm water is shut off from the tropics, then paradoxically, the temperatures in Western Europe could plummet, even conceivably entering another ice age in that part of the planet. Now, something else that seems likely to be a consequence of global warming is shifts in global precipitation patterns. So, predictions are that places like North Africa and the Great Plains of the U.S. could receive less precipitation, whereas the southwestern U.S. could receive more. Let's look at a map of predictions. This is another NOAA-generated map based on its climate models that predicts that by the end of the 21st century, we could see patterns like these, with the brown areas receiving less rainfall and the deep blue areas receiving more rainfall. So the northeastern part of the U.S. would receive more, but much of the western and southern parts of the country would receive less. Notice also North Africa and Central Africa becoming drier. Based on these NOAA climate models, we might also expect to see this happen to the northern polar ice cap. Look at its extent in 1885. It had already shrunk by 1985, but if we go another century to 2085, it's virtually gone. So in the southeastern part of the U.S., for example, we might expect these areas in red to be inundated as sea level rises as a consequence of things like polar ice cap melt and thermal expansion of seawater. So from the upper left to the lower right, we see this progression of areas being inundated by the ocean. One last map based on predictions of climate models is this one, showing a predicted change in the frequency and direction of strong storms. Notice as you go from the upper to the lower map how many more lines there are, indicating that we can expect more severe storms off the coast of eastern North America. And at this point, we'll close for today, and we will continue on with our topic of pollution next time.